Am I audible? Okay. Okay. Screen is visible now. Okay. So good afternoon all. Let's start today's lecture. So in the last lecture, the two types already we have studied. The first one is the closed loop bit synchronizer, and second is our early late bit synchronizer. Okay. With the help of block diagram, we have studied overall working for a closed loop bit synchronizer as well as the early late. Okay. Now for a carrier synchronization, now in today's lecture we will start with the carrier synchronization. So already we know the idea how this carrier synchronization means. The coherent detection happens in bandpass modulation technique. Okay. So in bandpass modulation technique, instead of recovering the clock, here we are going to recover the carrier frequency fc. Okay, but if we compare the carrier synchronization in digital communication, okay, so with the analog communication, so try to understand this comparison first. Okay. Now in analog communication, while studying the coherent detection means the carrier synchronization in double sideband suppressed carrier and single sideband suppressed carrier. So in both the types, close double sideband suppressed carrier and single sideband suppressed carrier, we use a separate circuit at the receiver side to generate the carrier frequency, synchronized carrier frequency. Okay, but in a digital communication, here we have to recover the carrier frequency from the received signal. This is the received signal. This is the transmitter receiver part. This is the receiver part. So this is the signal we received. That is not the BPSK signal. For example, BPSK signal is here. One of the modulation technique in digital communication, binary phase shift keying. So this is the mathematical equation of BPSK. So from this BPSK signal itself, we have to recover carrier. Okay. Now let's see how do you recover here. So this received BPSK signal, here we have to connect with, first of all, the phase comparator one. So that is the combination of multiplier and low pass filter. Okay. Similarly, the same signal BPSK signal we have to connect to the second phase comparator. That is nothing but again the same combination, multiplier and low pass filter. Okay. Now this is the first connection to the phase comparator, to the phase comparator. Now the second input to these phase comparators is from voltage control oscillator. So voltage control oscillator will generate a random carrier frequency. Okay, so that random carrier frequency we have to connect to the 90-degree phase shifted to phase comparator 1 and directly connected to the phase comparator 2 below phase comparator. Okay. Now whatever the output of multiplier and low pass filters, what is the output here? We will get simple formulas are there. It is cos A, this is cos B. So use the formula cos A into cos B, so that result we will get here at the first comparator. Similarly here, cos A into sin B or sin A into cos B, these formulas we have to use, and the resultant output here we will get. Okay. So after that, the resultant output of phase comparator 1 and phase comparator 2, we have to multiply. And whatever the multiplication is there, so from that multiplication we will get one control voltage here. So that is VC, and that control voltage we are going to use to correct the exactly carrier frequency. Okay, so that will be filter out control voltage, and that control voltage is going to use to correct the carrier frequency. Once we will get the correct carrier frequencies, from this point we will get exactly the recovered carrier frequency. Okay. So that is the simple working of carrier synchronization or Costos loop. The method is Costos loop. That is a Costos loop, this and this one. So it is Costos loop. Okay. So only two mathematical equations you have to understand: cos A into cos B and cos A into sin B. These two formulas we have to use. So whatever the resultant output is there. Okay. So after multiplying again, so one voltage we will get. Okay. So that voltage is going to use to correct or to get the correct carrier frequency. So this simple working is there of carrier synchronization. Is it okay? Let me know whether you have understood or not. Is it okay? Am I audible? Okay. Okay, so this is all about the type of carrier synchronization. Okay, that is nothing but a Costos loop that we used. Okay, in analog communication also we use the Costos loop. Okay, but the difference is what? Here, from the received signal itself, we have to recover the carrier in digital communication. That is the only difference you have to understand. Okay, so this is all about the different type of synchronization that we have studied. Okay, so that is the carrier synchronization. Now let's study the next topic, the data formats. Okay, data formats also called as the data encoding. So let's first of all go through what are the properties of line coding or data coding or data format. There are different names we can use: data format, data encoding, or line coding. Okay, now here data formats or data encoding or line coding means what? Just I'm giving an example. Let's say we have data 10, okay, and we have to represent this data. Means we have to represent some voltage level for bit 1 and bit 0. So either I can represent bit 1 for this one and bit 0 like this, or I can represent like this, bit 1 and bit 0. Okay, so that is bit 1, this is bit 0. So these are the formats. This is the first format, this is second format. So there are different 7 to 8 formats to represent the data formats, to represent the data formats. Now question is why we are using the different line codes or data formats. Okay, so these are the properties. Let's see what happens, or we can say simple, the advantages of different data formats. Okay, now as the coding is done to make the more bits transmit on a single signal, okay, the bandwidth used much reduced. Okay, so that is the first advantage we can say. By using this type of data formats, bandwidth of the signal we can reduce. Okay, now for a given bandwidth the power is efficiently used. Okay, so the power efficiency also increases if you are using different data format. So that is the second advantage, power efficiency improves. Now third is the probability of error is much reduced. Error probability also reduces. Means if you are transmitting 101, so sometimes due to the distortion in the transmission line, we could receive like this 100 like this. Okay, so there is a difference between these two bits. At the transmitter we transmitted 1, but at the received we received 0. Instead of 1 we received 0. So in such a situation, if you are using different data formats, so it will correct the actual bit automatically, it will correct the actual bit. Okay, so such type of probability of error is reduced. Okay, so that is the next advantage. Error detection is done, and bipolar 2 has to correction capability. Error detection means, as I said here, this is the error detection. Instead of 1, if you are receiving 0, so that 0 again we will correct as a 1. So that is the correction capability. Okay, power density is much favorable. We will see later what is the exactly power density. Okay, the timing content is adequate. Okay, and this is very important. The long strings of 1 and 0 is avoided to maintain the transparency. Already we know what happens if you transmit long sequence of ones and zeros. So there may be a major probability to lose the synchronization if you have a long sequence of ones and zeros. But if you have a long sequence of ones and zeros, and if you represent different type of data formats, so there may be not means we can avoid the loss of synchronization if you are using a proper data format to represent a long sequence of 1 and zeros. So these are the some properties of data formats. Okay, so basically the data formats is nothing but what? It's the encoding process of using various patterns of voltage or currents to represent one and zeros of the digital signal on a transmission line. So as I said, simply encoding or data formatting nothing but what? To represent the voltage, plus voltage, minus voltage, zero voltage for bit 1 and bit 0. Okay, so the representation of some voltage level to bit 1 and bit 0 is nothing but what? Data formatting or encoding. Okay, so commonly or basically there are these types: unipolar, polar, bipolar, and Manchester. Okay, one more type is there, split phase Manchester. We will see study later, and polar quaternary. Okay, but basically there are these types: unipolar, polar, bipolar, and Manchester. Okay, now let's see one by one. Unipolar means single polarity. Unipolar means single polarity. Single polarity. Polar means both the polarity, positive and negative. Bipolar means both the polarity, but alternate representation is there. We will see later. Okay, so try to understand. Once you understand this nomenclature, it is very easy to draw that formats. Okay, unipolar, as a in the first word itself indicates, unipolar means single polarity. Polar means both the polarity, positive and negative, and bipolar means also both polarity, positive and negative, but the representation is quite different as compared to the polar. Okay, and split phase Manchester is a one of the type. Okay, now let's see one by one. Now let's see one by one. So let's start with the unipolar signaling. Unipolar signaling. Okay. So here to understand, we will take a reference of clock signal. This is the first clock signal. Okay. This is the second, third, fourth, and so on. Okay. So you can see one clock means what? It is T on. It is T on and it is T off. So T on and T off is nothing but what? One clock. It is one clock. Okay, so you can see in one clock, one bit is generating. So this is the simple data we have. This is simple data. So it is 1 0 1 0 0 0 1 triple 1 and 0. Okay, now this is the 0 voltage and this is a plus V voltage. So unipolar NRZ means what? Now here unipolar signaling. So unipolar signaling in the first type, it is unipolar NRZ. It is unipolar NRZ. So in unipolar also there are two types, unipolar NRZ and unipolar RZ. So NRZ means what? Non-return to zero. Unipolar NRZ means what? Non-return to zero. Try to understand what is by NRZ. NRZ means non-return to zero. So non-return to zero means what? I'm writing here non-return to zero. Okay, so non-return to zero means what? We have a some voltage level for bit 1. Okay, so it is not returning to zero, means the sum part of means whole part duration from bit 1, it representing the voltage level. Okay, therefore it is called as the non-return to zero. Okay, and for bit 0 it is zero voltage. So simply for bit 1 we have a voltage and bit 0 it is a zero voltage. So simply it is non-return to zero, also called as on-off keying. Also called as what? On-off keying. On-off keying means what? If bit 1 is there, voltage is there. If bit 0 is there, 0 is there. Simple. Okay, so that is unipolar NRZ. Only one polarity positive and it is non-return to zero. Okay, so this is the first unipolar NRZ format. Now let's see some advantage and disadvantage. So advantage of unipolar NRZ is it is very simple. As you have seen here, for bit 1 it is plus V voltage, and for bit 0 it is for bit 0 it is 0. Okay, so it is very simple. Lesser bandwidth is required. Requirement is very less to transmit such type of data format. What is the disadvantage? The disadvantage of unipolar NRZ are no error correction is done. Error correction यहाँ पे possible नहीं होता. ठीक है. After that, the presence of low frequency components may cause the signal drop. If there are some low frequency components are there, so it may be a loss of synchronization. That is the next point. The loss of synchronization likely to occur, especially when the long strings of ones and zeros are there. Especially when there are long strings of ones and zeros are there. Okay, so these are the some advantage and disadvantage of unipolar NRZ. Okay, now the next type is unipolar RZ, return to zero. Unipolar RZ, return to zero. Now look here carefully. This is the clock signal again. In the one clock we have to generate one bit. Okay, so this is a simple example of data. Same data 1 0 1 double 0 triple 1 0. Now how do you represent return to zero? Now look here carefully. What is by return to zero? So this is a complete one duration TB. So you can see for bit 1 we have unipolar means single polarity. So only for bit 1 we will have a single polarity, that is positive voltage, that is V voltage. But the half of the part of bit 1 will return to zero. This is called as return to zero. Half of the bit 1 part represent the voltage level, and after that the half part will return to zero. So that is called as return to zero. And for bit 0 it is 0. Okay, again you can see for next bit 1 half part representing the voltage and next part return to 0. Okay, for bit 0 it is 0. Again for bit 1 half part representing the voltage level, half part return to 0. So this is called as return to 0, means unipolar return to 0, single polarity return to 0 for bit 1. Simple. Now let's see some advantage and disadvantage. Advantage is very simple. After that, the spatial line represent at the symbol rate can be used as a clock. Okay, that is the next advantage. What is the disadvantage here? No error correction is done under unipolar RZ. Occupies twice the bandwidth as unipolar NRZ. Bandwidth increase ho jati if you are using unipolar NRZ signal. Okay, the signal drops is caused at the place where the signal is non-red 0 hertz. Okay, means low frequency are there, the signal may drops. So these are the some disadvantage of. Now let me explain the second one. Occupy the twice the bandwidth as a unipolar NRZ. Twice the bandwidth means what? Actually here, what happens in unipolar, this is the unipolar NRZ signal. Okay, so here overall band, bit rate is TB. So if we take the inverse of this one, we will get the, for example, if TB is 1 millisecond. Okay, so if we take the frequency here, F, so here, how much we will get here? 1 kilohertz. 1 kilohertz. So this is the bandwidth we can say for this particular signal, 1 kilohertz. Okay, now here the overall signal is representing here TB. Okay, but the half part is returned to 0. So only the pulse we have from 0.2 TB by 2. Okay, so if it is 1 millisecond, so 0.5 millisecond we will get. 0.5 millisecond we will get. Okay, so if you inverse this value, if you take the inverse 0.5 millisecond, so F here we will get here 2 kilohertz. Okay, we will get the 2 kilohertz. So that is the meaning of this point. Occupies the twice the bandwidth as a unipolar NRZ. That's the meaning of that particular sentence. Now let's see the polar signaling. So as I said, polar signaling means what? Positive and negative, both the polarity we have to use to represent bit 1 and bit 0. Okay, now let's see first type, polar NRZ. Polar NRZ. Okay, polar NRZ. So polar NRZ means what? Both the polarity. This is the clock. In one clock we have to generate one bit. So that is a simple example. It is given common example. Okay, now let's see what is the polar NRZ. So polar NRZ means both the polarity, positive and negative. Okay, so for bit 1, obviously this is the timeline I can draw. Yeah, okay, so both the polarity here, it is positive voltage for bit 1, and for bit 0 it is negative voltage. So that is positive for bit 1 and negative for bit 0. Simple. Okay, so that is polar NRZ. Again, for bit 1 it's a positive voltage, and for bit 0 negative voltage. Okay, so this is polar NRZ. Now let's see some advantages. It is simple. No low frequency components are present when we represent any signal. So low frequency जो components होते हैं वो disappear हो जाते हैं. ठीक है? After that, disadvantage, no error correction is done by using this polar NRZ, and the signal drops is caused at the places where this signal is non-zero at 0 hertz, means low frequency hertz. Okay, so that this is the disadvantage of this polar NRZ. Now again, next one is what? Polar RZ. Polar RZ, return to 0. So as I said, return to 0 means half part of the signal will return to 0. So you can see here polarity, both the polarity we have positive and negative. So you can see for bit 1, so half part is returned to 0. Now for bit 0, again we have negative polarity, but half part will return to 0, like this, return to 0. Okay, so again here bit 1 return to 0, bit 0 negative value return to 0. So this is the polar RZ. This is the polar RZ. Okay, this is polar RZ, like that. So simple polar RZ signal. So it is simple. No low frequency components are present. Let's see the disadvantage. No error correction is done. Occupies the twice bandwidth. As I said, whenever there is a return to 0, so it occupies the twice the bandwidth. Fine. After that, the signal same disadvantage that we have seen in polar NRZ. Okay, only one extra disadvantage is here. Polar RZ is occupies the twice the bandwidth of the signal. Now next step is bipolar signaling. I hope it is clear. Or is it okay? The signaling data formats, because these are very simple formats. Just you have to understand the nomenclature that we are going to use here. Is it okay? Okay. Are you getting the proper formats here, how to draw? Because exam में क्या होगा, एक particular sequence will be there and for that particular sequence you have to draw the data formats. Means question would be like this, for a given bit pattern draw the following data formats. So वहाँ पे 4-5 data formats रहेंगे, so based on that you have to draw. Okay, but follow the process here like this, जहाँ पे मैंने जैसे mention किया हुआ है. First of all, you have to draw here the clock signal. Okay, this is the clock signal initially you have to draw, and after that you have to draw a basic signal जो कि numerical में दिया होगा, for which sequence you have to draw. Okay, and after that you have to draw the resultant output based on this one. Okay, so up till now what we have studied: unipolar NRZ, unipolar RZ. Okay, after that polar NRZ, polar RZ. 4 patterns already we have studied. Now let's see next one, the bipolar signaling. So bipolar signaling means it is again bipolar, plus and minus, but the difference is what here. This is an encoding technique which has a 3 voltage level, namely positive, negative and 0. So such signal is called as the DO binary signal. Okay, so bipolar means positive negative होगा, उसके साथ 0 भी voltage होगा. पोलर में क्या होता था, only positive and negative voltage level in polar signal. Okay, but in bipolar signaling positive भी रहेगा, negative भी रहेगा और 0 भी रहेगा. The 3 levels we have to use there, bipolar signaling. Okay, so therefore it is called as the alternating mark inversion, AMI. ये बाद में देखेंगे why it is called the alternating mark inversion. Okay, now let's see one example. So again we will have 2 types, bipolar NRZ, bipolar RZ. Okay, this is the clock signal, this is the data. Now let's see what is the bipolar NRZ. Now look carefully, it is very important. Here we have a sequence 1 0 1 0 0 triple 1 0. Okay, so you can see for bit this is 0 voltage, it is plus, it is minus V. Okay, so I'm drawing this timeline T. Okay, now for bit 1 we have a voltage V. Okay, now for bit 0 it is 0 voltage, but what I said, in bipolar 3 polarities are there, plus, minus and 0. Okay, so positive for bit 1, 0 for bit 0, but next bit जो 1 आएगा उसकी polarity inverse हो जाएगी, that is minus voltage here. So therefore it is called as AMI, alternative mark inversion. Alternate means what? Whatever the polarity of previous one is there, so next one की जो polarity होगी वो inverse हो जाएगी. So here previous one voltage level is plus voltage, so next one जो आएगा bit 1, so for that one we have to use the negative voltage. Okay, for 0 it is 0 voltage. Now again there is a next bit is 1, so again we have plus voltage. नेक्स्ट बिट अगेन 1, सो प्रीवियसली प्लस था तो यहाँ पे माइनस होगा. अगेन नेक्स्ट बिट इज 1, सो यहाँ पे अगेन प्लस वोल्टेज आएगा. ओके, सो देयर आर 3 पोलैरिटीज, प्लस, पॉजिटिव, नेगेटिव एंड 0. ओके, सो दिस इज द बाइपोलर NRZ. ओके, नाउ बाइपोलर RZ मींस व्हाट? रिटर्न टू 0. सो ऑब्वियसली जो बीट 1 जहां पे भी वोल्टेज पल्स होगा वहां पे आधा पार्ट कहां पे जाएगा? टू रिटर्न टू 0. 0 के लिए इट इज 0. अगेन फॉर नेक्स्ट वन हाफ पार्ट विल गोस टू रिटर्न टू 0. Again here it is return to 0 like this. Wherever there is a voltage level, either it is plus or negative, so that voltage level part will return to 0. So this is bipolar NRZ and RZ. So bipolar NRZ also called as AMI. AMI NRZ. Okay, this is AMI NRZ. AMI NRZ and this is AMI RZ. This is AMI RZ. Okay, so this is bipolar and ये बहुत famous है examination point of view. Now let's see the advantages and disadvantages. It is simple. No low frequency components are present. Occupies low bandwidth than a unipolar and polar NRZ scheme. This technique is suitable for transmission over the AC coupled lines. Alternate current. Okay, as a signal dropping does not occur here. This is important. Whatever the patterns that we have seen in previously, so there that overcome over here. A signal error detection capability is present in this method. Which one? Signal error detection. What is the disadvantage here? The long strings of data causes loss of synchronization. So here that is the only one disadvantage. If there is a long sequence of ones and zeros, so loss of synchronization may be possible. Okay, this is bipolar bipolar NRZ and RZ. Okay. Now next pattern is split phase Manchester. Next pattern is split phase Manchester. Okay. So here I have not mentioned the clock and data here directly. I have mentioned here the signaling part. So if there is a, for example, if there is a bit 1, and this is the timeline, so if there's a bit 1, so split phase Manchester means what? Bit 1 half part positive sign and half part negative sign. Okay. नाम क्या है इसका? स्प्लिट फेज मैनचेस्टर, स्प्लिट फेज हो रहा है. ओके, सो फॉर बीट 0 के लिए कैसे आएगा? हाफ पार्ट नेगेटिव, हाफ पार्ट पॉजिटिव, like this. So therefore it is called a split phase Manchester. You can see for bit 0 it is, just wait, yeah, for bit 0 you can see the half part negative, half part positive, half part negative, half part positive. Okay, actually this is not correct. I'm drawing here correctly signal for this particular signal. This is not correct actually. Okay, I'm drawing here the corrected format. So what is the sequence here? 0 1 0 0 1, for example. Okay, so for bit is plus V voltage, minus V voltage. Okay, and these are the intervals, for example. Okay, so for bit 0 it will start from negative, end at positive for bit 0. Okay, similarly for bit 1 it will start with the positive, end with the negative. Okay, again next bit is 0, so it start with the negative, end with the positive. Okay, again next bit is 0, so it start with the negative, end with the positive. So next bit is 1, start with the positive, end with the negative. So this is the split phase Manchester. Just remember how to represent bit 1. So bit 1 we are representing like this, start with positive, end with negative. And for bit 0, here for bit 0, start with negative, end with positive. Okay, so this is the split phase Manchester. Fine. And the last type is polar quaternary NRZ. So polar quaternary NRZ means up till now we have seen single bit representation voltage level. Single bit representation voltage level. Okay. Now here we are going to see how do you represent the group of bits voltage level. Okay. So in polar quaternary NRZ we represent 2-bit group representation. So these are the possible combinations. So for 0 0, okay, for 0 0 it is, so there are different formats. So for 0 0 it is plus 1, for 0 1 it is plus 3 voltage, and 1 0 it is minus 1, and 1 1 it is minus 3. Okay, आप इसका उल्टा भी कर सकते हो, आप इसका उल्टा भी कर सकते हो. Okay, so it is for previous level positive and previous level negative. Okay, so one of the format you can use either this representation or this representation. Okay, so here it is going to use, okay, here it is going to use okay, let me take one example, you will get a clear idea here. The split phase Manchester. Yeah, so what is the combination we have? 0 0 0 1 1 0 and 1 1. Okay, so for example let's say we have a voltage A. Okay, now to represent this combination group of bits, to represent the group of bits here, for 0 0 0 1 1 0 and 1 1. Okay, so what we will do, we will use for 0 0 minus 3a divided by 2, minus 3a divided by 2. Okay, similarly for 1 1 we will use 3a divided by 2. Okay, and for 0 1 here we will use minus a divided by 2, and for 1 0 here we will use plus a divided by 2. So a you can put any voltage, 2 volt, 3 volt, 5 volt, 6 volt, like that. Okay, now let's say we have the data 1 0. Okay, after that 1 1 0 1 0 0 1 1. this is the input signal we have, but we know this signal we have to represent by using polar quaternary format. So here I'm drawing the 4 levels. First of all, it is a by 2, and here it is 3a by 2, and here it is minus a by 2, and here it is minus 3a by 2. Okay, now first two bits are 1 0, so first two bits are 1 0, so for 1 0 it is a by 2 voltage level is there, so it is a by 2. Okay, for it is 1 0. Okay, next two bits are 1 1, so for 1 1 it is 3a by 2, so here it is 3a by 2 for 1 1. Okay, next bit it is 0 1, so for 0 1 the voltage level it is minus a by 2, so where it is minus a by 2 here, so here it is 0 1. Okay, after that the next bit is 0 0, so for 0 0 we have minus 3a by 2, so here we have minus 3a by 2, so here we have minus 3a by 2 for 0 0. Next bit is again, here it is 1 1, so for 1 it is 3a by 2, so here it is 3a by 2. Okay, so this is the polar quaternary signal. So in polar quaternary signal, 2 bits we are going to combine to represent the voltage levels. Okay, so I hope it is clear. If you have any doubt, then let me know. Is it okay? Is it okay? Okay, fine. Okay, so in the next lecture, this is the time domain analysis. In the next lecture, we will see the frequency domain analysis. Okay, means the power spectral density function. The power spectral density function. So I think it is okay for today's lecture. So we will meet in the next lecture then. Okay, so this is the time domain analysis. In next lecture, we will see the frequency domain analysis. Okay, and one of the practical is based on this particular topic. जो आपका नेक्स्ट प्रैक्टिकल होगा वो इस टॉपिक के ऊपर ही होगा, द स्टडी ऑफ डिफरेंट लाइन कोड्स. Okay, so till then, goodbye, take care.